Let's talk about section 7.1 angles. Okay. Um, First, we need to talk about what standard position is. Most of the measurements that we've done in math have been in two directions, horizontal and vertical, but the real world has more than two directions. And so we'll kind of talk about what standard position is today, and that's how we work with angles now. An angle is a pair of two rays that share an endpoint. It's called a vertex, just like this. Okay. The measure of the angle is the amount of rotation from one ray to the other ray, right, from initial to terminal ray. All of the angles below have the same measurement, about 75 degrees or 83.3 of a right percent of a right angle. Okay, they just have different lengths. When we talk about standard position, we are starting here on the x-axis and moving in a counterclock position, rotation, and the terminal side is the other side of the angle or the other ray that creates that angle. Okay, notice we have those quadrants labeled like we've seen at this point. If we haven't seen that yet, this is how we label our sections of the graph. We start on the top right and then move counterclockwise. We have quadrants 1, 2, 3, and 4. Okay. Now there's a lot of units for measuring angles. You have revolutions, you have angle measurements, you have radian measurements. There's a ton of different ways. We call one revolution one full circle. We had Greeks measuring things with right angles, so four right angles was one revolution. Today, we really focus on two pi radians being one revolution, and we'll talk about radians more today. All of these are going to help us measure angles with any level of accuracy, but the difference is that sometimes it's more convenient to want to use one than the other. Um, so let's start with arc length. So arc length, which is labeled as S, is the distance traveled around a circle by a given angle. It is completely dependent on the radius. If you have the part over the whole times the circumference, that is going to represent S, your arc length, okay? Your circumference of a circle is 2 pi r. We've definitely seen that before. Now, it depends on how you're measuring theta. If you're doing it in revolutions, it'll look different than degrees. It'll look different than in radians. So if theta is measured in revolutions, we have the arc length is equal to 2 pi theta r. Okay, 2 pi theta r. So if we're interested in finding um, theta is one revolution, we would have S equals 2 pi r, right? Because this would turn into a 1. Okay. If we were working with degrees, we would be dividing by 180 degrees, okay, to account for that relationship in the circle. If we are plugging in 90, we would have S equals I R times 90 over 180, which would simplify to pi R over 2, okay? And then finally, if we're working with radians, this is pi, right? This is the approximation for pi. We would have S equals theta r, or S equals 3.1415 r. Okay. We're eventually going to use radians more than degrees, so you are going to become more familiar with it as we do it. And I would start familiarizing yourself with those radian measures soon. Now, well, there's two ways to measure things. We can measure degrees, we can measure radians, like I've mentioned before at this point. You can do either. We're going to practice using both. You're going to put the angle in standard position at 0, 0. Okay. And then you're going to start moving it in the counterclockwise direction. And then if you want to measure S, then you're going to find pi times theta times 1 over 180, because on the unit circle, which is what we're going to be using, the radius will equal 1. Okay, so r is equal to 1. Now, if we're measuring in radians, we have S equals theta R. Okay, and again, R is going to be 1 on the unit circle. Okay. Now, let's look at this example. Identify the angle in degrees and in radians, which spans an arc length of S equals 5 pi over 6. Okay, so let's start by doing this in radians. So from earlier, we had S equals theta R, right? We know that R is going to equal 1. Okay, so we also know that S is 5 pi over 6. So notice that just by replacing R with 1, we have already figured out what the radian measure is. Okay. If we want to do this in degrees, we have S equals theta over 360 times the circumference of 2 pi r. Okay. We can go ahead and replace r with a 1, and then we have 5 pi over 6 equals 2 pi theta over 360. And at this point, we just need to solve for theta, right? So we can simplify. Those i's will go away, and the rest we need to just kind of divide out. We're going to get theta equal to 150 degrees. Okay. Next up, we have areas of sectors. That's another geometric property that is really dependent on angle. We will again use part of a whole times the area of a circle, right? This right here is your area of a circle if we're working with degrees. Okay, so you'll end up with theta times pi times r squared divided by 360. So that part over the whole is right here. Okay, and then the rest is your area. Now, let's plug in 45 degrees for theta and see what happens. Okay, we're going to have 45 out of 360 times pi r squared. Okay. All we need to do is simplify 45 over 360. We don't have a given radius in this situation, so we would have pi r squared over 8 as our solution, units squared. If we did this in radians, it looks slightly different. Instead of using 360, we would use just pi r squared times 2 pi. Okay. All right, so now for plugging in that 2 pi, we have 2 pi r squared all over 2, or pi r squared. Okay, and again, we don't have a radius, so we can't go beyond that. Okay. Let's find the arc length and sector area spanned by an angle of pi over 2 radians with a radius of 12 centimeters. Let's start with our arc length of S equals theta times r. Okay, we know that the angle is pi over 2. We know the radius is 12, so we end up with 6 pi centimeters. Okay. For the area, we have the equation pi r squared over 2 because we're in radians. Let's go ahead and plug in everything we've got. Okay, all divided by 2. We're going to go ahead and simplify. This will be 144 pi over 4, or 36 pi centimeters squared. Okay. Now, if you want to convert between degrees and radians, the conversion is right here. 180 degrees is equal to pi radians. Okay, so if you're converting between the two, you can stack them as a fraction depending on what you need in either direction. So in this case, 60 degrees would become 60 times 180 underneath pi, and then we would have pi over 3 radians. And if we had radians, we would want to multiply by that reciprocal. We want pi on the bottom and 180 on the top, and we would get 210 degrees. Let's briefly talk about quadrantal angles. Quadrantal angles are at the 90-degree turns, okay? Um, there are technically unlimited ones, right? You could have infinite loops around a circle. Um, so starting at the very beginning, we have 0 degrees and 0 radians. If we move up, we have 90 or pi over 2. If we move 2 right angles, we'll have a straight line at 180 degrees or at pi radians. If we move 3 right angles, we'll be at 270 degrees or 3 pi over 2 radians. And if we come all the way back around, we'll finish at 360 degrees or 2 pi radians. Now, is the angle -5 pi a quadrantal angle? It is, right? Let me show you what that might look like. Now, notice that it's negative, which means we're actually going to go clockwise. Here is -1, -2, -3, -4, and -5. Okay, let me come back in here with a different color to kind of show you that. So here is -1 pi. Here is -3 pi. And then here is -5 pi. Here is -2 pi. And here is -4 pi. Okay. So yes, -5 pi is a quadrantal angle. It is in the same position as -1 pi, -3 pi, and if we were to go in the positive direction, it would be the same position as +1 pi. Okay. All right. Coterminal angles. So in that previous example, we saw that we rotated, um, and by continuing that same rotation, we end up in the same position no matter how many times we did that. So there's infinitely many different angle measures with the same terminal ray. Those are called coterminal angles. And coterminal angles. Um, you can find them in degrees, you can find them in radians. No matter which way you do it, that K represents that constant that you're multiplying by how many times you're rotating. Okay, so for angles, it's plus 360K. For radians, it's 2 pi k. So for example, if I have this arbitrary angle here, whatever it is, theta, okay, I can loop around once, okay, and that would also have the same um, angle measurement, or that would be in the same position as the black angle, and it could continue, right? I could do another loop, and that would also have that same position. Okay, and those are all just coterminal angles of the black angle. Okay, let's find a coterminal angle between 0 and 360 for alpha is equal to -2500. Okay, so we're just gonna add or subtract 360 from this value, depending on if it's a positive or negative. In this case, it is -2500. Okay, so -2500 plus 360 times k. Okay. Um, in this case, I'm trying to think of a number that would get me into a positive value between 0 and 360. And I know that 7 might do that. If you need to, you can just add 360 until you get into that acceptable area in that range. That's totally fine. We're going to get 20 degrees. Okay. Now, if we want to convert that to radians, we have 20 degrees times 1 oops, pi over 180, which is going to be pi over 9 radians. Okay. Let's find a coterminal angle between 0 and 2 pi for beta. So now we are in radians. That means we're going to have to add or subtract 2 pi depending on if it's positive or negative value. In this case, it is positive. So we have 30. Whoops, I did not mean to rotate. We have 31 pi over 6, and we want to subtract 2 pi. Okay. Now we need to get a common denominator. So I'm going to rewrite that as 31 pi over 6 minus 12 pi over 6. And I'm just going to go ahead and subtract it once. That's going to get me 19 pi over 6. I'm going to go ahead and subtract another iteration of the circle, which does get me to 7 pi over 6 radians. Okay. If I want to convert from radians, I'm going to multiply by 180 over pi to get rid of those pi's, top and bottom, and I'm going to get 210 degrees. Okay. And last, we're also going to talk about linear and angular speed, which will be much more relevant when you take a physics class, but we kind of touch on it slightly in pre-cal. And there are multiple ways to calculate speed. Okay, there is linear speed, and there is linear velocity, and there's angular velocity. So, looking at the scenario, there's a gear. It has a radius of 14 centimeters, and it's rotating 5 degrees every second. How fast is it turning? There are two ways to answer that. It could be angular or it could be linear. Okay. Angular is measuring how quickly the object is rotating, including the middle of the object. Okay, so the entire thing is rotating. And we are going to calculate this in degrees per second. And I'm going to write SEC in all of these. Degrees per second, radians per second, revolutions per second, and then revolutions per minute. So let's go ahead and start with degrees per second. The good news is that information was given to us, 5 degrees per second. Not much else we have to do there. In the second part, we do need to convert from degrees to radians. So 5 degrees times pi over 180 is going to equal pi over 36 radians. Okay. And we have seconds already, so this is your final answer. Pi over 36 radians per second. Okay. If we want revolutions per second, it is most convenient for us to go ahead and use the radian measure. So I'll just go ahead and bring down that pi over 36. Okay, we are going to multiply by the conversion for radians and revolutions. Okay, so radians will be on the bottom, revolutions will be on top. Okay, one revolution will be 2 pi radians because it's one full circle. Okay, one loop is 2 pi radians. Okay. And then when we multiply all that out, we're going to have one revolution over 36 times 2, which is 72 seconds. Okay. Notice that the pi's will cancel out. Okay. And then finally, in revolutions per minute, all we're doing is taking this previous answer and converting it to minutes. So we have one revolution per 72 seconds, and there are 60 seconds in 1 minute. Okay. So we will end up with 60 over 72 revolutions per minute. If you wanted to get a decimal, that's totally fine. It's approximately 8.833 repeating. Either one works. Okay. Okay. Then we have linear velocity. Okay, linear velocity measures how quickly the outer edge of the object is moving. It can be miles per hour, meters per second, inches per second, all those things. Okay. Linear speed is the arc length per unit time, so slightly different. All right. So for centimeters per second, let's go ahead and start with what we know. We know that we are working with radians or with degrees. In this case, it's a little bit easier to just go ahead and use the radian measure. So I'll go ahead and pull that for my second answer. So we have pi over 36. Okay. That's going to be multiplied by my 14 centimeters per radian. Okay. Let me talk to you about why that's happening. Okay. We talked about how in radians, let me come over here. In radians, that the arc length is equal to theta. Okay. And so if you have a radius of 14, okay, that's also 1 radian. Okay. That's also 1 radian. So 14 centimeters is proportional to that 1 radian in this problem. Okay. We'll go ahead and multiply and simplify. We will get 7 pi over 18 centimeters per second. If we want, whoops, I hope it didn't delete everything. Oh, it did. Okay. Um, Let me briefly write down what we just wrote. 7 pi over 18 centimeters per second. 1 radian equals 14 centimeters because S equals theta. Okay. We had pi rad over 36 seconds multiplied by 14 centimeters over 1 radian. Okay. Now, in meters per second, all we need to do is convert from centimeters to meters. So we'll do a quick unit conversion. We have 7 pi over 18 centimeters over seconds. And there are 100 centimeters in 1 meter. Everything else is still fine. We can simplify and get 7 pi over 1800, right? So that denominator is getting much larger. And finally, in kilometers per hour, we need to convert meters to kilometers as well as seconds to hours. So I'll go ahead and take 7 pi over 1800 meters seconds. Okay. Um, Meters on the bottom, kilometers on top. There are 1,000 meters in 1 kilometer, and there are 60 squared seconds in 1 hour. So 60 seconds in a minute and 60 minutes in an hour. So I'll just combine those. Okay. And we are going to get a decimal. It's very small. That suggests that this gear is not doing any sort of heavy machinery work, probably. It's definitely not moving your car. And we get 0.0439823 kilometers per hour. Okay. Briefly, I do want to also talk to you about different ways to use the linear velocity equation. You could also think of it as uh, theta r over t, right? Because that is an equation, S equals theta r, which also relates to that theta over t times r over 1, which was our omega from earlier. Okay. So the other option, okay, the other option is going to be that V equals omega times R. Okay, there's multiple ways to do this, and that's what we did here. We had omega times R. So we ended up using this equation without me even telling you that that's what we ended up doing. Okay. All righty.